All right, so yesterday we started chapter 18. We said that the historical definition of an aromatic compound was something that's smelly. Today we're going to talk a lot more about that modern definition, that an aromatic compound, according to modern terminology, is a planar ring system with 4n plus 2 pi electrons that are delocalized. And then we went into the nomenclature. Make sure that you guys review this nomenclature before the exam, because this may be used in naming conventions, not only on sapling, but on third term exams or the ACS exam as well. But let's take a look at this 4n plus 2 definition. This is also known as Huckels Rule. So let's define this as clearly as possible. So molecules are aromatic if they have 4n plus 2 electrons located in p orbitals that are aligned in a ring system. So this is a little bit more specific. So let's take a look at just the classic example of benzene. And then we'll try to count how many electrons are in p orbitals. So if we look at benzene, we've got 2 electrons here. We've got 2 electrons over here. And we've got 2 electrons over here. All of those are in the p orbitals. So we would say this is 6 electrons, right? A lot of people get confused by that 4n plus 2 terminology. What do you think the n stands for?
Number of double bonds,
or just some integer, right? It could be 0, it could be 1, it could be 2, it could be 3, it could be up to whatever number you want it to be. So if we look at this in a mathematical sense, 4n plus 2 can be 6 when n equals 1, but n in this case needs to be an integer. You can't have n be 0.5. It needs to be a whole number, not a fraction. Does that make sense? Let's do a couple of example problems, and I want you guys to tell me if the molecules I'm drawing are aromatic or if they're not aromatic. And I want you guys to count electrons in these systems too. So this molecule is very famous. We'll do some 5-membered ring molecules. We'll do benzene again just for good measure. And then we'll do an octagon that's fully conjugated. So I'll give you guys a minute to work on this, but check with your neighbor and see if you can identify which of these is aromatic. It's 4n plus 2.
Is that all it says? 1 plus 2?
Mm-hmm.
Not equal everything, just 1 plus 2?
Yep. Yeah, as long as the number of electrons equals 4n plus 2 for your p orbitals in the ring system. I'm going to actually add one more in here. Let's do this one too. You guys are super quiet today. I don't know if you guys feel this way, but I think the weather is getting to everybody now. I've noticed like everybody in the Puget Sound region's like on edge a little bit. Like the rain needs to stop. All right, do you guys want to try working through some of these? All right, let's do the first one that I've labeled A. Does anybody think that's aromatic? How many electrons do we have in the p orbitals in the ring system? 4, right? So we could go ahead and we could say this is 4 electrons. If you actually do molecular modeling on this, you'll also find out that it's planar. So does this follow the 4n plus 2 rule? So 4n plus 2 is the total number of pi electrons necessary for a molecule to be aromatic. So if we go and we say, you know what, 4n plus 2 in this case needs to equal 4, right? Is there an integer that satisfies this equation?
Oh, 0.
Is there?
Oh, wait. He works up the mark.
So in this case, right?
I still don't understand the rule.
So Huckels Rule says that this equation has to have some sort of integer solution for the number of electrons in the p system, right? So in this case, we don't have 4n plus 2 pi electrons, so this is not an aromatic molecule. In fact, it falls into a different category known as anti-aromatic. An anti-aromatic system is similar to an aromatic system, but instead of having 4n plus 2 pi electrons, it has 4n pi electrons. So anti-aromatic molecules have 4n electrons. Anti-aromatic molecules are incredibly unstable. They tend to be hard to isolate. They'll react very, very quickly. In order to make this molecule, you can actually read about it in your textbook. They had to trap it in a molecular cage so that it couldn't react with anything else. It was a pretty crazy tour de force of chemistry, and the chemist that worked on it was actually awarded the Nobel Prize for his investigation on aromatic systems. Okay, what about the next one? How many pi electrons do we have for B? 6. That lone pair actually gets counted because it's in a p orbital in order for it to delocalize, right? Do you guys remember talking about resonance? We said that if a lone pair can delocalize, it will delocalize, which means that this carbon up here is actually sp2, and that these electrons must be in a p orbital in order for delocalization to occur. So this is going back to first term concepts. So in this case, we've got 6 total electrons. This is also planar. And does this follow the 4n plus 2 rule? Is there some integer where 4n plus 2 equals 6? Yeah. So you could have 1 as your integer, and that would fulfill that equation. So in this case, this molecule is aromatic. This has that special stabilization of about 150-ish kilojoules per mole. This is a really stable molecule despite it being an anion. In fact, this is commonly used as a ligand in inorganic chemistry. It will kind of stack with a metal. It's pretty cool. All right, what about the next one? How many pi electrons do we have? 4. Okay, so if we look at this, we've got 4 electrons. All right, this could also be considered planar. So Would this be aromatic or anti-aromatic? Anti-aromatic. In fact, this molecule isn't very stable at all, and it will do a bunch of funky chemistry. All right, what about D? Okay, so we could say there's 4 pi electrons in there, right? Is this molecule planar?
Not all of them.
Does anybody see a problem, though?
SP3 on the top.
SP3 on the top, right? So this molecule has an SP3 hybridized carbon up here. Does that mean we have p orbitals going all the way around the ring anymore? No, there's no p orbital in an SP3 hybridized carbon. Therefore, this can't be aromatic. You can think of this as a planar molecule, but it's actually, in this case, considered non-aromatic.
But it is still planar.
Yeah. All right. And then with E, we already did this one already. That's just benzene. We said it has 6 pi electrons. We know that benzene's planar. And we know that it's aromatic. All right, what about F? How many total pi electrons do we have? 8. Is there any integer that satisfies that 4m plus 2 rule? No. So, in this case, it's a little bit tricky. People are often tempted to say, well, is it anti-aromatic then, right? It follows the 4n rule, which we said satisfies anti-aromatic compounds. The reality is slightly more complicated than that. Because anti-aromatic compounds are so unstable, this actually will adopt a kind of odd-looking conformation, and I'm going to try my best to draw it. This has a fancy name called a tub. So this is kind of our side-on tub view, where the 2 ends actually fold up, which actually distorts this out of planarity, because if it's planar, it would be anti-aromatic. And we know anti-aromatic molecules are highly unstable. So in this case, let's make a note that this is not planar to avoid anti-aromaticity. That means that this is just simply non-aromatic. If we look at our other anti-aromatic molecules, so for example, I've labeled it as C and A, those have no choice but to be stuck in that planar configuration. They can't orient themselves out of planarity. Therefore, they are forced to be anti-aromatic. The molecule I've labeled as F, that cyclooctatetraene, can actually contort itself to get out of planarity to relieve some of that instability. Does that make sense? The other weird thing is if you go through textbooks or through the internet, there's this common thought that anti-aromatic molecules are so unstable that you really can't isolate them. You can only observe them in these really bizarre situations like trapped in a molecular cage or at negative 150 degrees Kelvin or something like that. The reality is we're actually getting to the point where we can make some semi-stable anti-aromatic molecules, and they're really, really interesting as potentially useful for organic photovoltaics. Does anybody know why? What do you think an anti-aromatic molecule really wants?
Give away electrons.
Yeah, give away or accept electrons, right? So if you think about a semiconductor, have any of you guys learned about semiconductors? So with semiconductors, you have a P and an N-type semiconductor, right? And the whole goal is to move electrons, right? So anti-aromatic molecules are really novel because they can accept or lose electrons in order to form their aromatic state. And so there's a lot of interest right now in forming anti-aromatic molecules for some of these advanced photovoltaics. Kind of neat. Yeah, the big thing, so if you look at normal photovoltaics, they have P and N-type semiconductors, but they're inorganic, right? Yeah. The big problem with our silicon-based photovoltaics is they're really expensive. If you've ever gone and priced out a solar panel, they're not cheap because they have to be single crystal silicon. However, if we get organic semiconductors and organic photovoltaics, you can actually paint it on your house, you could paint it even on roads, you could paint it on wherever you want. And it wouldn't be as efficient as single crystal silicon, but it'd be so easy and cheap to manufacture, and you could put it anywhere, that the cost savings would actually play into your favor. So there's a lot of cool chemistry coming out right now about all this. Let's take a look at some of these more complicated examples, though. All right, with aromatic heterocycles, you have to pay a little bit more attention. And we saw this yesterday with pyridine, right? So this is our classic base that we've been using a lot. And yesterday I showed you guys that you can view this essentially as a molecule that's laid on its side. So I'm going to do my best to draw this on its side like I did yesterday. And if we do this, we can see that p orbital system is delocalized across all the carbons. Or I should say carbons and nitrogens. Oh my goodness. So we've got p orbitals up, up, up. Whoa, that looks funny. And then yesterday I said this lone pair is kind of cool because it's stuck out here in an sp2 lobe. However, we've got a pi bond system that's delocalized across the ring, and when we show it in our 2D conformation, we show it as alternating double single bonds, but in reality we know all of it's delocalized across the p system. All right, so now the question is, how many electrons are in the p system? 6, right? This is a common mistake students will make, is when they look at pyridine, they're like, well, why aren't you counting the lone pair as being a part of the system? The simple answer is it's not in a p orbital, right? Huckels Rule says we only count electrons that are in adjacent p orbitals. We do not count this guy over here. So don't count non-p orbital electrons. Oh no. So if we look at this one, pyridine has 6 pi electrons, therefore it is aromatic. Right? Do you guys see that? Let's do a different example. This one's a little bit more complicated now. Let's compare pyridine to its 5-membered counterpart. This is called pyrrole. And if we look at pyrrole, how many electrons are in the p orbital system? 4 or 6? Ah. This is debatable, right? Let's try to do that same molecular orbital view that we've been doing. So I'm going to have a carbon, nitrogen, and then I'll put the back 2 carbons over here. Oh my goodness. Let me try to clean this up a little. Okay, so we've got these p orbitals sticking up. Oh, let me do the same color diagram. The hydrogen, in this case, is actually occupying an sp2 lobe, right? So let's make a little note here. This is connected via sp2 lobe. And our lone pair electrons that we have shown in our 2D drawing are actually hanging out in that p orbital. And then we've got this pi bond right here and this pi bond right here. So if we count the total electrons in the pi system, how many do we have? 6. And this makes sense too, right? If we think back to first term, I said electrons that can delocalize will delocalize. We can delocalize these electrons using resonance arrow pushing, right? I could just continue pushing this over around the ring. So anytime you can do these electron pushing arrows, you need to consider those electrons as a part of a p orbital, and you have to count them in your system.
Is that why it wouldn't be sp3 hybridized?
Yeah, exactly. That's why that nitrogen in parole is not sp3 hybridized. If it were sp3 hybridized, that lone pair wouldn't be able to delocalize. And we know delocalization helps stabilize molecules.
So then in the pyridine example above it, because we couldn't have arrow push without breaking off tat or putting a lone pair back into the system, it wouldn't work.
That's a good point. So with pyridine, if we try to do resonance arrow pushing with this lone pair, we'd be breaking some octet rules and making super unallowed resonance structures, right? So we don't want to break any of those rules we learned in first term. You guys want to challenge one?
I have a quick question on that.
Yeah.
So does the term aromatic kind of loosely mean like stable then, as opposed to anti-aromatic, even though that one can turn into a sub?
Yeah, aromatic means that it's got that stabilization energy of about 150 kilojoules per mole. So this one is also aromatic because that lone pair is counted in the p orbital system. So let's do a challenging one. And I want you to check with your neighbor about this one. Let's do furan. Is furan aromatic?
No.
And for the broader question, what's the hybridization of that oxygen?
That's good.
So check with your neighbor too and see if you guys agree.
Here's what if you do this, times 3, it'll be like that. It's not going to be too much closer to linear because there could be a double bond here and double bond here, so it has.
What's that?
We count the lone pairs and try to figure out what they are.
If the lone pair is in a p orbital, it is counted, right?
What? That's one time.
One that's not. And then one part that is.
So I'm going to just copy this and replace that nitrogen with an oxygen. But the big question we've got right now is, what is the hybridization?
It has two things attached to it, so I would want to say SP. There's those two lone pairs that are there too. But isn't SP?
But I figured because these were both got partial double bond characters, and it would make it too beneficial. That's just too bad. Not with the two simple. It would, like if that was a card.
They're not double bonds, so they wouldn't be fully bound. They would be fully
That's just what I'm thinking.
Raise your, or give me a thumbs up if you think you got it. Raise your thumbs. All right, let's see a show of hands. How many of you think it's aromatic? A few people? Does anybody want to share why? What do you think?
I think one of the lone pairs on oxygen is in a P and the other is in ST.
So you think one's in a P and one's in SP or SP2?
Yeah, that's what
SP2? Yeah, I would agree. So if we look at this one, it's a little bit weird. but one of the lone pairs is in this p orbital, and then the other lone pair is actually hanging out in this sp2 lobe. So that means that this oxygen is sp2 hybridized. Why is it not sp, or why can it not be sp?
That'd be linear.
It would have to be linear. Yeah, that's a good reason. The other problem too is if we look at the neighboring carbons, they're all sp2. Typically, in order to have something like an sp atom, you have to have an adjacent sp atom to form that triple bond. But in this case, we don't even have that option. So sp is bad for a couple of reasons. A, it can't be linear, and B, there's not an adjacent sp atom nearby to form a triple bond with. So if we look at this, it's kind of weird to think about, but how many electrons are in the p orbitals? 6. So all of these have 6 pi electrons. We can only count one of the lone pairs. We can't count both of them because one of the lone pairs isn't in a p orbital. And if you think about this in terms of resonance structures, right, if you try to do arrow pushing, you can move one of those lone pairs with resonance, but you can't move both of them at the same time without violating some sort of octet rule. So that's a simple check as well. All right, you guys want to try a couple more? Let's do this one. Let's do this one. And then everybody's favorite ring size, the 7-membered ring.
No. This is not Canada. Okay, this one.
Oh my goodness.
You'll get there.
I'll get there. Thank you for the moral support. All right. I still don't like it.
Can we never have a 7-membered ring on it?
Maybe I'll make that an extra credit problem. Draw a perfect 7-membered ring. I'll have like a no-name after that. Perfect no-name will be like 2 extra credit points.
Remind me of green bottle kits. Yeah, well, that's do an SP2 with
But I would comment. I'd be like, so that's slowly get rid.
And I'll do one more down here.
What is that?
And double bonds. This is histamine.
We haven't done it.
Yep.
Or non-ring.
So let's check all of these and see if these are aromatic or non-aromatic or anti-aromatic.
And remember your waste. This next one. If it's not a ring, because that's double bond, you have to have you have the 6.
Does anybody think the top one's aromatic? Does anybody think it's not aromatic? Oh man. Looks like Brian and Andy are in a fight here.
Always.
Always.
Does anybody want to share why they think it's not aromatic? Grace?
Well, they're not all, there's pi bonds, 3 of them, but they're not all in the ring. And if you try to drag down the top pi bond electrons and put them on that carbon, you'd have a negative carbon and a positive carbon, which is pointless to draw.
Exactly. So Grace is saying that this pi bond is what's referred to as exocyclic. Exocyclic pi bonds don't count. So this molecule can't be considered aromatic because if we look at the ring system, there isn't the correct number of electrons in there. So this is not aromatic. Oh. What about the next one? Do you guys think it's aromatic?
No,
Oh, wait.
I don't think so.
I see some nodding.
I'm just guessing shooting.
Oh.
I'll give you guys a hint here. Let's do some arrow pushing, right? A valid resonance structure could be pushing electrons up to that upper oxygen. If we do that, right, now all of a sudden this oxygen would have a negative charge. This carbon's positive. Now is it aromatic? Yeah, it's got 6 pi electrons in that ring system. It's got all adjacent p orbitals. So in this case, this is aromatic. So like I said, use your resonance arrow pushing to your advantage. Try to push electrons around and see if that fulfills that 4n plus 2 rule. So in this case, even though that pi bond is coming off of the ring, it doesn't really matter because we're still satisfying the 4n plus 2 rule. All right, histamine's the tricky one. How many of you guys feel comfortable with histidine? Or, sorry, histamine.
Kind of makes me uncomfortable.
Makes you uncomfortable?
Swelling.
The swelling, the puffy eyes.
Yeah.
How many electrons are in that ring system? Well, let's do a little bit of analysis of those lone pairs because we know lone pairs can be deceiving. All right, this lone pair, can that lone pair delocalize?
Yes.
Yeah, you can push those electrons around, right? So that means that these can, or I shouldn't say can, they are in a p orbital. Simply because we know they can delocalize. All right, what about these?
No. They're sticking out sideways.
Yeah, exactly. These are in an sp2 lobe. You can't move them around with resonance without breaking a lot of rules. So in this case, these are not in a p orbital. So if we count the number of electrons in this ring system, how many are there? 6. So this would be considered aromatic, right? This is following all of the rules. I know this can be confusing, but there are a lot of good practice problems in your book that I would recommend going through in case you just want to see more examples, and especially some of the odd ones. Try to hit as many practice problems in the book as possible. All right, we've got 10 more minutes. Let's try to do a couple of the reactions. The good news is they're pretty similar to reactions we've seen. And the only reactions that are covered in this chapter are reactions at the benzylic position. And the benzylic position is very special. It's a lot like an allylic position, where we said allylic carbons tend to be really reactive towards things like radical halogenation. In this case, a benzylic position is just that carbon that's attached to a benzene ring. And why do these tend to be more reactive? Because of resonance, right? You don't know the answer, just say resonance. So these are really unusually reactive because of resonance, and I'll show you guys a cool trick you can do with benzylic carbons. And we're not even going to cover this reaction mechanism, which is nice. Let's say we've got this molecule right here. What's this molecule called? Toluene or methylbenzene, if you want to sound funny. You can actually convert this directly into a carboxylic acid. And what's this molecule called? Benzoic acid. In order to do this, all you need to do is throw chromic acid at it. No, it's not green, but it works. And this works really well. So you can functionalize a carbon into a carbonyl group, and we know we can reduce carboxylic acids to an alcohol, and then we've got a bunch of reactions we can do with alcohols. The cool thing is, if we look at the oxidation here, it goes from -3 to an oxidation of +3. So this is a 6-electron oxidation reaction. You can really oxidize benzylic carbons. You can also do this same reaction if you want to be more green. By using potassium permanganate.
If they run it cold.
No, in this case you don't have to run it cold. You can actually run this pretty hot. However, this is a 2-step reaction now. You crank up the heat, and then step 2, you have to protonate your acid by using another, or you have to protonate your carboxylic acid by using another strong mineral acid. All right, the other kind of cool thing is you're not limited to just toluene. Let's say we've got ethylbenzene, and we do one of these oxidation conditions. You can still make benzoic acid. In this process, you lose any of your other carbons that aren't benzylic. The only surviving carbon is going to be your benzylic carbon. The most important thing to remember, though, is that this only works when you have protons coming off of that benzylic position. If you try to do this same reaction with tert-butylbenzene, you're kind of stuck. You get no reaction. You have to have alpha protons, right? So in this case, you've got these alpha protons, which means that this will work. This one has no alpha protons.
What kind of reactions though?
These are still just oxidation reactions, but we're not going to get into the mechanisms behind them. What about isopropyl benzene? Can you oxidize isopropyl benzene?
Yes.
Yeah, and you can still make benzoic acid. The one problem with these reactions is if you have any other functional groups that can get oxidized, they will too. So for example, if you've got an alcohol and you do these reactions, you will also oxidize an exterior alcohol. So let's do an example of that. So let's say I've got this compound, and I'm going to do Na2Cr2O7, H2SO4, and water. What will the product be?
Super benzoic acid.
Super benzoic acid.
Yeah, carboxylic acid.
That top isopropyl group's going to get converted into a carboxylic acid. And then down here, you're going to oxidize that alcohol to a carboxylic acid as well. So you have to watch out for that. Does that make sense? There's also one last reaction I want to show you guys, and then we'll call it quits for the day. This is free radical bromination. And if you've got a benzylic carbon, you can essentially treat it like an allylic carbon. And what if we want to brominate our benzylic position? What reagent could we use?
Yes, and molecular bromine.
Not quite. What do we use for allylic bromination?
Oh, that.
NBS,
NBS.
right? So benzylic positions and allylic positions behave very, very similarly. So you can use NBS, which is that N-bromosuccinimide, and you can use heat. This will work on any benzylic position as long as you have alpha protons, right? So if you have tert-butyl benzene, you don't have alpha protons, there's nothing that you can brominate there. But if you have isopropyl benzene, you can, which is kind of neat. One thing I will say is refer to, was it chapter 11? For the mechanism. The mechanism is the exact same as an allylic bromination. However, we don't want to break aromaticity, so that your exclusive product will be that benzylic bromination. You won't have bromine coming off of the ring system itself, because if you did that, you'd lose aromaticity.
Does this work for other aromatics?
It works for other aromatics as well. However, as in your textbook, you will really only see it done with benzylic carbons. All right, if you guys want, you can get started on the pod. And then next week when we come back, we'll kind of finish up chapter 18, and there's only, I think, 1 or 2 more reactions we're going to cover.
How do you, what happens